Here's a perfectly nice system of two equations in two unknowns that we'll use to illustrate some basic principles of solving linear equations. And those principles will generalize to larger and more complicated settings. Your instinct is probably now telling you that we should add the first equation to the second, so that the x and the minus x may cancel. We follow this instinct, and we add equation 1 to equation 2. We keep track of equation 1 so as not to lose information. In equation 2, the x's cancel, y plus 2y equals 3y, and 4 plus 7 equals 11. It would be nice to get rid of this 3, so we multiply row 2 by a third. First equation stays the same for posterity, and the second equation becomes y equals 11 thirds. We have solved for y, so we're halfway done, hooray! One could here plug the 11 thirds back into equation 1 and solve for x. That would give us the correct answer. But the method is not generalizable or efficient. We instead take our cue from the first step, where we used one equation to simplify matters. In the first step, we used the x in equation 1 to get rid of the negative x in equation 2. Here, we're going to use the y in equation 2 to get rid of the 2y in equation 1, thereby solving for x. So we add negative 2 times equation 2 to equation 1. Equation 2 stays the same. There's no need to mess with that. In equation 1, the x is unchanged, 2y minus 2y is no y, and the 4 picks up a negative 2 times 11 over 3. We have now solved our system. X equals 4 minus 22 over 3, which is negative 10 over 3, and y equals 11 over 3. And we can check that we have the right answer by plugging x and y back into the original equation. We meditate on our example to generalize the wisdom we learned from it. We performed here two different kinds of operations on the rows of the system of linear equations that we'll call row operations. The first operation was to add a multiple of one row to another. We did that in the first step, where we added one row to another, and we did that in the third step, where we added negative 2 times one row to another. The other row operation that we did in the second step was to multiply a row by a scalar, which is what we call numbers. And we want that scalar to be non-zero because multiplying by 0 is silly. With these two row operations in hand, we can now tackle bigger and better examples, like this nice system of 4 linear equations in 5 unknowns. Remember how, in the smaller example, we first used the variable in the top left to eliminate the x below it. Similarly, in this example, we're going to use the x1 in the top left to get rid of all the x1s below it. We add 2 times equation 1 to equation 2 to eliminate the negative 2x1. Equation 1 stays the same, and equation 2 becomes negative x4 plus 2x5 equals negative 1. To get rid of 3x1 in equation 3, we add negative 3 times equation 1 to equation 3, which becomes 2x2 plus 2x3 plus 4x4 minus 2x5 equals 4. Finally, we get rid of the x1 in equation 4 by adding negative 1 times equation 1 to equation 4. And equation 4 becomes 2x2 plus 2x3 plus 3x4. That's an x4, not an x5. I'll correct it in a sec. There's no x5 here, equals 3. Notice how we've gone from the original 4 by 5 system to a system of 3 equations in 4 unknowns. We continue with the row operations as before, and we use the top left variable x2 to get rid of the x2s below it. But there is no x2 in the top left slot here. To circumvent that problem, we can switch rows 2 and 3. Let's quickly add that to our repertoire of row operations. We can switch 2 rows. Equation 1 hasn't changed. The new equation 2 is the old equation 3, and the new equation 3 is the old equation 2. Equation 4 stays the same. And that's an x4, not an x5. Now that we have a top left variable to eliminate the variables below, we add -1 times equation 2 to equation 4. Equations 1, 2, and 3 stay the same. And equation 4 becomes -x4 plus 2x5 equals -1. We've gone from a 4x5 system to a 3x4 system, and now to a 2x2 system of linear equations. So now we can use the -x4 in the top left corner to get rid of the x4 below it. And we add -1 times equation 3 to equation 4. As is our habit, we rewrite equations 1, 2, and 3. Equation 4 is completely eliminated by equation 3. We write 0 equals 0 to remind ourselves that there used to be an equation there. We can think of 0 equals 0 as follows. Equation 4 originally contained information that was redundant and that was already contained in the 3 equations above it. Before we continue with our solution, we pause here briefly to speculate on an alternate universe. What if the lower right 2 in the original system of equations had been a 5? Well, if we'd followed the exact same sequence of row operations, then the 3 in the lower right corner below it would have been a 6. And the 3 below that would have been a 6. The -1 in the lower right corner of step 4 would have been a 2. And the 0 in the lower right corner of step 5 would have been a 3. In other words, if we'd had a 5 instead of a 2 in the original system, then at this stage we would have the equation 0 equals 3. And there's no values that the variables x1 through x5 can take that can possibly satisfy the equation 0 equals 3. In that case, our system of linear equations cannot possibly have a solution. The equation 0 equals 3 cannot possibly be satisfied. Pause to make a quick definition. A system of linear equations is called consistent if it has at least one solution, and it's called inconsistent if it has no solutions. We go back to the original reality and 0 equals 0. At the comparable stage of the simpler example, we multiplied by appropriate scalars to make coefficients equal to 1. Following suit here, we want to change the 2 and the -1 to 1s. So we multiply equation 2 by a half and equation 3 by -1. Equation 1 stays the same. The x2 in equation 2 and x4 in equation 3 both have coefficient 1, and equation 4 is still 0 equals 0. We look again for inspiration in the original example. At the comparable stage, we used the lower equation to eliminate coefficients in the equations above. Here, we can use the x2 to get rid of the -2x2, and the x4 to get rid of the 2x4 and the -3x4 above them. Starting with x4, we add -2 times equation 3 to equation 2, and 3 times equation 3 to equation 1. Equation 1 becomes x1 minus 2x2 plus 2x3, no x4, minus 5x5 equals 2, and equation 2 becomes x2 plus x3, no x4, plus 3x5 equals 0. Equations 3 and 4 stay the same. Finally, we get rid of the -2x2 in equation 1 by adding 2 times equation 2 to equation 1. So equation 1 becomes x1, no x2, plus 4x3, still no x4, plus x5 equals 2. And equations 2, 3, and 4 stay the same. It may not look like it, but at this stage we're done. We just need to establish a new language framework that will help us read off all the solutions. We say a system of linear equations is in echelon form if the first non-zero entry in each row is to the right of the first non-zero entry in the row above it. For instance, all these systems on the left-hand side are not in echelon form, because there are some first non-zero entries that are not to the right of the ones above them, like pretty much all the rows in the first system, the x2 in the second system, and the negative x4 in the last system. On the other hand, notice how the fifth system is in echelon form, because the first non-zero entry in each row is to the right of the first non-zero entry in the row above it, giving us this pleasing staircase silhouette. Similarly, the other three systems on the right-hand side are also in echelon form, because each row starts to the right of the one above it. We define a pivot as a first non-zero coefficient of a system of linear equations in echelon form. Here our system is in echelon form, and so we look at the first non-zero entry in each row. The 1, 2, and negative 1 are pivots. The next system is also in echelon form, but all the pivots equal 1. That was in fact the point of the row operations, to force all the pivots to become 1. For the left-hand side systems, we can't speak of pivots yet because they're not in echelon form. Next, we define a basic variable as a variable corresponding to a pivot. Here we're in echelon form. Since x1, x2, and x4 correspond to pivots, they are the basic variables of our system. x3 and x5 have no pivots, so they're not basic. We'll call such variables not corresponding to pivots free variables. Note that basic and free are names we call variables regardless of the system being in echelon form or not, but we need echelon form to tell the variables apart. Finally, a system of linear equations is in reduced echelon form if the following three conditions hold. It is in echelon form, all the pivots equal 1, and all the entries above as well as below the pivots equal 0. Let's look at the echelon forms in our example. The top right system is in echelon form, but not in reduced echelon form because not all the pivots equal 1. In the next system, the pivots do equal 1, but the entries above the pivots are not all 0. We're closer to reduced echelon form here, because the entries above x4 are 0, but not above x2. And finally, we get to reduced echelon form, because we're in echelon form, all the pivots equal 1, and the entries above the pivots all equal 0. The great thing about reduced echelon form is that we can read all the solutions to a system of linear equations from it by writing each of the basic variables in terms of only the free variables. Here in reduced echelon form, our basic variables are x1, x2, and x4, and each appears in just one row because the entries above the pivots equal 0. Therefore, x1 will be writable in terms of just x3 and x5 without the use of x2 and x4, and the same holds for x2. And x4 will be writable in terms of only x5. We're ready to write the basic variables in terms of the free ones. We solve our system by specifying what each variable can equal. The free variables can equal whatever they want. That's why they're free. We indicate that freedom by saying x3 equals s and x5 equals t. Now we read off the solutions for x1 from the reduced echelon form system. x1 equals 2 minus 4s minus t. Similarly, x2 equals negative x3 minus 3x5, or negative s minus 3t. x4 equals 2x5, or 2t, and with that, we've found all solutions to our system of linear equations by writing each of the basic variables in terms of the free ones. This system has infinitely many solutions, one for each specific value the free variables take. Before finishing, I want to make one last observation. This alternate universe system, where the 2 was a 5, had no solutions, so we could have stopped at this stage of echelon form and declared that the system was inconsistent. In fact, the only way inconsistency can happen is when we get a row in echelon form of the form 0 equals non-zero, since otherwise we can always proceed to reduced echelon form this way and find the general solution as we did. So we record our final observation. The only way a system of linear equations is inconsistent is if in echelon form, there's a row of the form 0 equals non-zero. The only way this system of linear equations would have been inconsistent is if we'd gotten a 0 equals something other than 0 here. 0 equals 0 is perfectly fine. So having a 2 here gives us a consistent system, whereas having a 5, or really anything other than a 2, would have resulted in a 0 equals non-zero in echelon form, and hence inconsistency. In a best-case scenario, we would have had all zeros on the right-hand side. Since then, there is no amount of row reduction that would have changed all these zeros into non-zeros, and hence there's no way we could have gotten 0 equals non-zero in echelon form. Congratulations! Now you know how to find all the solutions to any system of linear equations through the process of row reduction.